Good morning. Okay, we're going to look at the lab for separation of a mixture that we're going to be doing the week of the 21st, I believe. Yes, the 21st. So this is our second in-lab lab, and we're going to be talking before we begin lab about how this ties into lecture. Now, we did mixtures. We talked about mixtures in Chapter 1 lecture. So at this point, I'm just going to kind of review this. You all have this memorized already, so, you know. Mixtures are physical combinations of two or more pure substances. These substances can be in varying proportions. In other words, if I have a mixture of salt and sugar, every child's favorite game with their mom, I can either have 90% salt and 10% sugar, or even amounts of sugar and salt, or mostly sugar and a little bit of salt. And it's still a mixture of sugar and salt. So this can be in various proportions, whereas a compound, as we know, has definite proportions. So a mixture is very different from a compound. It is not a pure substance. It is a physical combination of two or more pure substances. We have two different types of mixtures. One's heterogeneous, and with a heterogeneous mixture, you can see the different parts. You can see the different parts. It's non-uniform in appearance. It's frequently non-uniform in texture. You can definitely tell that it's a mixture. I can have a mixture of paper clips and chalk, and you can definitely see it's a heterogeneous mixture. I have more than one substance. Can you see that? I'll hold it up.
No, we can.
Okay? Heterogeneous mixture. A homogeneous mixture is something that's uniform in appearance, and you can't distinguish the parts. And our typical example of this is saltwater solutions. These are aqueous solutions. Salt dissolved in water. Now that doesn't have to be sodium chloride. If you've begun to look at your Chapter 2 videos, which you definitely should be almost through them, just saying, salt is any ionic compound that has a cation that's not hydrogen plus and an anion that's not oxide or hydroxide. So salts can dissolve in water. Not all of them, but almost all of them can dissolve in water. And you can't tell that it's not water. It doesn't look like anything but water. We also have solid homogeneous mixtures, and these are alloys. My favorite one is white gold, because that's what my wedding ring is. And it's literally a combination of gold, which is gold colored, and silver, which is silver colored, and in a certain proportion when you mix them together, they look like white gold. And that's an alloy. Bronze, brass, those are alloys as well. The gaseous mixtures are cool because it doesn't matter what gases you put together, it always forms a homogeneous mixture. That's a physical property of every single gas, always forms a homogeneous mixture. Of course, we are breathing a homogeneous mixture, that being air, and if we have a homogeneous mixture of primarily nitrogen and a tiny little bit of oxygen, that's what they store apples under to keep them fresh so they don't oxidize, but you can't breathe it. If you breathe it, you die, because there's not sufficient oxygen to support life. Okay, so heterogeneous mixtures and homogeneous mixtures, we're going to be dealing with a heterogeneous mixture. And our heterogeneous mixture is going to be made up of silicon dioxide, sodium chloride, and ammonium chloride. Now, you know these better as sand, salt, and ammonium chloride. You don't know that one. But, okay. And our photographer is going to show you a close-up of the substance and, or the mixture, and you can see that it's a heterogeneous mixture. You can see the various parts. Thank you, photographer. All right, so we have two objectives for today. Two objectives for this week, I should say. The first is that we're going to separate those components. We're going to take the sand, the salt, table salt, and ammonium chloride, and separate them into their individual pure substances. So that's the first thing. Now, we're going to do this via physical means, and in order to do this via physical means, we have to figure out which physical properties are different enough that they can be used. Okay, so I have, for the sake of time, I'm not going to list many, many physical properties. I'm only going to list the two that are important. And one of them is water solubility. Now, any of you who have been to the ocean know that table salt dissolves in water. Sand, better not. If sand dissolves in water, we have much bigger issues than lab. Ammonium chloride is also a soluble salt. So, I can see right away that using filtration, is this still in?
No, the string is your border.
Okay. Using filtration, so dissolving in water, and then filtration will separate sand from NaCl and NH4Cl. But these two are still combined. Okay, so that helps some, but it doesn't make everything separated. So let's look at something else. Let's look at melting point. Now, we all know that sand melts eventually into glass if it's pure enough and has some borosilicates in it. The melting point of silicon dioxide, and we looked it up this morning, is 1700 degrees Celsius. Good luck getting to that in general chemistry lab. Sorry, I'm not sick. The melting point of table salt is 801 degrees Celsius. Well, we can get to that in the oven that we have in the chemistry department. But it's pretty hard to get to that using a Bunsen burner. When we look up ammonium chloride, it says 340 degrees, and it says, has a little word sub next to it. Now, what does that mean? Well, that means that ammonium chloride sublimes, and I'm going to have to put it over here. Ammonium chloride sublimes at 340 degrees Celsius. Now, for those of you who've already read the lab, you know that sublimation means going from a solid phase to a gaseous phase without going through the liquid phase. And in fact, you can reverse this in something, this is called sublimation. The reverse of this is called deposition, where you literally can go from a gas to a solid without going through the liquid phase. So ammonium chloride sublimes. This is cool. You can heat a mixture of sand and salt and ammonium chloride and watch with a Bunsen burner and watch the ammonium chloride sublime. It's awesome. People tend to say it's smoke. It's smoking, Mrs. French. No, it's not. It's the ammonium chloride subliming. All kinds of white vapor escaping. So, that's cool because it sublimes at a temperature that's way below anything that salt, table salt, or sand is going to do anything. okay? It's really kind of cool. Now I'm going to step over to the side, so I'll be out of the video for a second. Don't go to sleep. Now yesterday, our photographer and Mr. Proetta performed this experiment, and they heated, we're going to pretend that's a beaker, and they heated the mixture in this and put this over the top. This was considerably cooler, the funnel, from the beaker, and so what happened was as the ammonium chloride sublimed, it hit this much cooler surface and it deposited on the surface. So that's kind of cool. Some of it got up here and some of it ends up going out into the hood. Probably if we looked in the hood, up above, we could see ammonium chloride. Okay, so that's not a good thing. So let's put this all together and see if we can figure out how we're going to separate these components. Well, I would recommend we get rid of the ammonium chloride first. Why not? Stick it over a Bunsen burner, see if you can catch some of the ammonium chloride so we don't have it all going into the atmosphere, you know, wiping out birds that are flying overhead. That really wouldn't happen. But anyway, let's get rid of the ammonium chloride. Poof, it's gone, okay? It actually takes a while for it to poof, but it'll be gone. Then we're left with just silicon dioxide and sodium chloride. Easy peasy, throw some water in, stir it up, filter it, got nice clean salt water, and we have sand. Dry them up. Why? Well, that's part two. Part two is we want to find the percent of each component. Each one of you is going to have a different composition, a different amount of sand and salt and ammonium chloride in your mixture, each one of you. So your job is not to figure out their sand, salt, and ammonium chloride. Your job is to figure out the percents. So how do we do that? Well, if you think back to your percent composition of a compound, we found the percent, and this was also in chapter 2, we found the percent oxygen in carbon dioxide. We found the percent carbon in glucose, etc. Okay? You can find a percent of a component in a mixture the same way. The percent of the component is equal to the mass of that component divided by the mass of the whole mixture. So your first thing is going to be the mass of the mixture. But this gives you a fraction. So times 100%. You're going to be doing this for sand and for salt and for ammonium chloride. You're going to find the mass of the dry sand, right? The mixture has dry sand. After you've filtered it, dissolved the salt in water, filtered it, that sand's going to be wet. So you got to dry it. The sodium chloride, you're going to find the mass of the sodium chloride. Well, after you've dissolved it in water and filtered it, it's going to be mostly water. You have to dry it. So you'll have the mass of the silicon dioxide, the mass of the sodium chloride. You'll have the mass of the, wait a minute. How are we going to find the mass of the ammonium chloride? Well, I suppose I could scrape it off of here and maybe use a paper clip or something to scrape it out of there. And then I could go into the hood and scrape it off the sides of the hood. And then I'd have to go up the hood and try to get that bird that was dead on the roof. And no, that's not going to work for just so many reasons. So how would I find the mass of the ammonium chloride? Well, remember, the mass of your mixture contains sand and salt and ammonium chloride. if you know the mass of the sand and salt, that leaves the wrong finger. Then you can figure out, by subtraction, the mass of the ammonium chloride. Okay? Once you do that, you find your 3 components, and you're golden. So you may be saying to me, Mrs. French, why not start with dissolving water and then blowing off the ammonium chloride and, well, first of all, we didn't design the experiment that way. We could do it that way, but it's a little more difficult, and you don't get that lovely ammonium chloride sublimation. It's going to be in water, so you see some vapor from water and very diluted ammonium chloride. It's not going to come across as obvious and as striking as it will if you sublime it first. So you could do it the other way, but it gets much more complicated, and we really want you to see sublimation. All right, so if you have any questions on the context of this and how we're relating it to lecture, please let your lab instructor know, and have fun in lab.